resolving power of simple microscope here. For simple microscope, from NCERT book only it is there. So I just picked up the discussion from there only. But we don't have any much numericals on it. I don't know why they have missed it. The discussion is not systematic even in NCERT book. Okay, there's an object, or this is some insect. It will subtend an angle, say phi, and there's a medium. If this medium is air, then you are going to put mu equal to 1. There's some liquid you can call it, or say medium. Its refractive index is mu. The diameter of the lens is capital D. Okay, we'll use same symbol, and there's a lens. I think there's only one lens, will become simple microscope, no? Okay, fine, this one. So the limit, the resolving limit. So here limit of resolution, we define it as dx is equal to 1.22 lambda 2 mu sine phi. What is the phi? Half cone angle subtended by the object at the lens. And what is the lambda? Wavelength of the light emitted by the object. So I think all objects what happen will not be self-luminous. Then what we do? We illuminate it from the background. Or the white light which is reflected by the object, that will become lambda. So what is lambda now? Lambda is the wavelength of light emitted, or better say, or so let it be emitted only. So how do it can emit? It cannot emit on its own. So I'll eliminate it. Wavelength of light emitted by object. What is mu? Refractive index of medium Ri of medium between object and lens. So if there is no medium, if it is air, then you're going to put mu equal to 1. Like this, the distance, there's the smallest distance of separation between the two objects which you can see from the simple microscope. Okay, this d theta, here we're bringing dx here, the limit of resolution. Means earlier you are unable to see, now with the help of this you can see it with the help of this lens, because it will increase the viewing angle. Okay, well, so like we are not understanding what you are saying. Okay, I'll give one diagram. If this is a lens, you have kept it two objects. I'll take like this. You have kept it two objects here. Then what happens? This lens will form an image, and that image will be seen by the eye. That image will be seen by the eye. So when that particular, and the separation between them is like a dx dash. When this particular lens can resolve it, when dx is less than dx, so dx of what depends upon the lens, so like it depends upon the mu and angle subtended, all that one. Or if you're getting confusion, so that this mu what will happen, you can also bring it like this here. But usually one object will be there. We never go for comparison. So therefore, you can also do like this. So in books, they didn't suggest it. So that they went for like this only, the diagram. I'll stick on to the book idea. This one. So like this, I'll find out the limit of resolution. So when the high EV is able to see the two distinct objects produced by this lens, when dx is less than dx dash. And now, if you remove the lens open, the eye says, I'm unable to see it. Okay, I think now able to get this. Human eye says that I'm able to see two objects. I'm able to see two objects. So this is happening because the limit of resolution is what, like less than dx dash. How to calculate the dx dash? I know separation. I know at what distance this particular object is kept from the lens. No, without this lens. Okay, if there is a I'll place this eye very near so that you will. No, this eye is here. You ask this eye, no. He says that I'm unable to see the two objects. I'm seeing one object only. Now tell me, like, what is the problem here now? What is the problem? The eye is having poor resolving power. By keeping the lens open, we are increasing the resolving power. So when do the eye will say after using the lens? Only when the limit of resolution provided by the lens, if it is less than that of the dx, that one dx dash, then it says I says yes, I'm able to see now. If he removes lens, he says that I'm unable to see it. Like this, for simple microscope, we define the reciprocal of this will become the resolving power. Okay, so the same concept is expanded for microscope here. Compound microscope, or just you can write only microscope. Then again, what is the criteria for microscope? If there are two objects are there, where if the eye say that I'm unable to see those two objects, then what happens when you see through microscope, if you're able to see means, then what you can say that the microscope is able to resolve. The microscope is able to resolve it. I'll start with the small diagram. Okay, I think I'll show the only one lens. There are two lenses are there, no? Okay, we'll keep it. This is objective. Eyepiece lens. So if it forms an image, this is called like this. Then you can say that the microscope is what happened, able to resolve it, no? Then if it forms only one image, sir, how come two objects, if they're kept and still you are saying one image, as it can happen? There's a microscope overall, objective and eyepiece are there. So this is F0, this eyepiece. Then here what will happen, as you keep on decrease the distance, then at one position what will happen, it will form only one image. As you keep on increase the distance, as we are able to see the two images. Even for the microscope, the same problem. So there is some conditions there. So that will define now the limit of resolution. So what is the limit of resolution for a microscope? That the reciprocal of that will become the resolving power. I think just only the formulas are very, very important. The rest all theory now I almost explained it. Shall I write formula for resolution limit or limit of resolution? I'll give one more diagram. This is eyepiece. This is objective. This is say some insect. Which has to be viewed, and here I'll take a bulb. Source of light. FO, FE, that one. Okay, so sorry, this is FE. This is FO. This is objective lens. This is eyepiece lens. And here is human eye. So now what is this? Again, the formula, the angle, the half cone angle subtended by it. This, let me call phi. And there's a refractive index of medium, mu. Usually liquid will be filled up here. So the limit of revolution, so we'll define like this. It is the smallest distance between, it is smaller distance between 2 point objects at which they can be just resolved by the same simple microscope only formula. I'm bringing it here. So that is dx, I'll write it. So there should be lambda by 2 mu sine theta. Mu of medium, there's a medium. Huh? So where that medium between objective and the specimen, this is called like a, rather than object, I'll call specimen. What is mu m? Ri of medium filled between objective lens and a specimen, not between the lenses. Between the lens is of no use. So this is one thing it's brought here. Lower the limit of resolution. If lower the limit of resolution, greater the resolving power. Lower the limit of, then what is resolving power? The reciprocal of that is what we'll call resolving power. This is a resolving power. So what is RP equal to 1 by dx? So this should be equal to 2 mu m sine phi, no, it is. Where that mu m sine phi is called as a numerical aperture. Numerical aperture. Tell me like, hey, what shall I do? So resolving power should be high, no? Limit of resolution should be low. Resolving power should be high. For resolving power to be high, if I don't bring any medium between the objective lens and the specimen, mu will be 1. Resolving power will decrease here. And what about this? The half cone angle subtended by the specimen at the objective lens. Half cone angle. Okay, if you want, you can write one more phi here, so that'll be easy for you. Half cone angle. Tell me, shall I bring it, the specimen, shall I bring it near to the objective or far away from objective? If I bring it nearer, sine phi value will increase, no? Resolving power will increase here. So I think all of you know microscope, this will be kept on some stand, no? Where you are able to move, no? And you can also move the objective. Eyepiece will be fixed here. Objective, you can move it. And this particular thing, the specimen itself, you can move it. What is the lambda now? What is the lambda? Lambda is light emitted by what, like a specimen. All specimens will not be luminous, no? So therefore, I'm going to illuminate it by a source of light. So what shall I prefer? Shall I go for blue light? So what are the things we can produce here? Yellow, blue, these are the, so, and red. So Vibgyor, if you take it, so in that what happened, the blue color light what happened is what practically I'm able to produce it, and also therefore in the microscope what happened, I'll illuminate by blue color light the specimen. From below what happened, it'll be kept on glass. Am I right? The specimen will be kept on a glass, and from the behind what happened, I'll illuminate it. So that will, so lower the lambda, greater the resolving power. I'm able to see things clearly. Again, the idea is like this only here. Again, the basic idea is like this. So the resolving power, again, there's a limit of resolution. So now, so what is that, like a window, the microscope will produce only one image if it is having a poor resolution or poor resolving power, or limit of resolution is very poor. So therefore, when designing microscope, it has to be taken care here. Okay, able to make it out. So there's one core idea of this one. I think I could have shown the derivation, not there for syllabus. I need around some 1 hour to bring this particular thing. So we have to take help of this diagram only by applying ray optics, everything, and again going for definition of like a diffraction. That one. So we can derive this. It's, I think it's not there in NCERT book also. Okay, in future, any time permits, I'll show it. How this has come. So telescope, no problem, because directly what happened, the objective of telescope will be like a slit of diffraction experiment. So therefore directly we are able to write it. Here we have to bring in, we are supposed to show proof. Because of time constraints, I'm directly wrote this one. So these are the, I think directly they may give these values, they may ask you. So, or they may test you with a limit of resolution. Tell me like a where that this separation dx, so shall I say dx is what, this one, no? So how you have to check it now? I think I gave earlier one more diagram. Yeah, it is like this, similar, the same approach of simple microscope only. Two objects which are there, okay, that will be given for us. And the limit of resolution, you are able to calculate. When the lens will able to resolve, when the limit of resolution of the lens, if it is less than the separation between the objects, it will resolve. If the limit of resolution of the instrument, if it is less than, if it is greater than the separation, the lens, what happened, the instrument is unable to resolve. For microscope, you have to think like this. Got the idea? So these are the, I think the numericals will be this much only, directly straightforward. They give separation between the objects. Then calculate the limit of resolution. What this limit of resolution depends upon? The wavelength of light, lambda will be given. The mu is what? Between the object and the lens here, this particular medium.